everybody. In this video we're going to discuss one more application of the Bernoulli equation, and before we go into the details of this application, I'd like to show this video. This is so the application is called liquid siphoning. If you're not familiar with this term, I think this video would be a good demonstration for you. And by the way, this is also one video that I made at home, so it's not like a sophisticated thing. What you see here before I play the video is a container that contains colored water. I just put color in this water to make it easy to observe, and this is I put it on a box here to be at a little bit high level. And there is another container in the bottom. It's an empty container. It doesn't contain any water. What I am doing here is I have a straw like what we use for drinking things, and I immerse it in water to fill it totally with water. So this is one important thing that we have to do. So first we fill it with water, and oops, I'm sorry. And there is something here about the straw. So yeah, it has like a U shape with one side taller than the other, but it has a U shape, and I am blocking the output here. So the side here is blocked so that the water will not flow until I release my finger. So now I release my finger, and what you see here is that there is a spontaneous flow of water from the top tank to the bottom tank along this this path that you see here, which is kind of strange. It's unexpected that why water will flow up and then down again. And the flow will continue until the water level is beneath the inlet of the of this straw. So it could have continued the flow if the straw is longer from this side. So this phenomena is called liquid siphoning, and we can explain this phenomena using Bernoulli equation. And this is just there are a couple of things that have to be satisfied, and the Bernoulli equation can explain why these two conditions must be satisfied. The first is that the surface of the liquid has to be higher than the effluent of the tube. So the effluent of the tube has to be at a lower level than the surface of the tube, and this is what we saw in the video. The other thing is that the tube cannot go directly down. It has to go up and then down. And this is the other thing. And there should be an initial flow. So there are should be three conditions. So there are two conditions that relate to the heights. So the tube has to go up and then down. I already put them here. The pipe must go to higher elevation than that of the source, then down to the desired discharge point, and that the initial flow has to be induced. So I induce the initial flow in my case by filling the tube with water, and the gravitational force started the flow. The liquid will flow by gravity to the tank in the bottom or the container at the bottom. So this induced an initial flow. In some cases, the initial flow is induced by sucking water or air from the tube. So any initial flow can cause this phenomena to happen, which is called siphoning. Okay, so to explain this phenomena, we have to apply Bernoulli equation. We have 3 points here: the surface of the liquid, the point at the very top part of the or the highest point on the tube, and the exit or the discharge point. We know that point 1 and 3 are open to the atmosphere, and that the surface of the liquid is going to have relatively small velocity, so we can consider the velocity here to be 0. We will call this the difference in height h1, and this difference in height h2. So between the surface and the discharge is h1, and between the surface and the top of the the maximum height of the tube is h2. So we can apply Bernoulli equation between points 1 and 3. And by applying Bernoulli equation, as we said, the pressures are equal, so you'll cancel out. The velocity here is 0. So we can find an expression for the velocity here in terms of the height, h1. And we can see that u3 is square root of 2g h1, which is an equation that we saw before. But the good thing, or the interesting thing here, is that the velocity will have a value, or a positive value, of course, or a real value, only if h1 is positive, which means that h1 has to be positive, or point 1 has to be above point 3. If the height or point 1 is at the same level or lower level than point 3, the siphoning is not going to happen. So this is or this explains the condition that we mentioned before. And by the way, from continuity equation we can tell that point 2 and 3 will have the same velocity because the same flow rate and incompressible flow in the same cross-section area. So it's the same velocity of point 2 as point 1. Now let's apply Bernoulli equation between points 1 and 2. So here we explained why point 3 has to be lower than point 1. Now by applying Bernoulli equation between points 1 and 2, we know the pressure here is atmospheric, the velocity is 0. We know nothing about point 2 except the height. So we can write the equation and put the data in the data that we have, and by rearranging the equation we can get an expression for the pressure at point 2. So if we calculate the pressure at point 2, you'll find something very interesting, that P2 is equal to the atmospheric pressure, which is the external pressure, which is the same pressure at point 1, by the way, minus rho g h2 minus this height times rho g minus half rho u2 square, which is this u2. Okay, so I'm sorry. So by this we'll find that this is telling us something, although we don't know the values of h2 or u2, but we know that they both are positive values. So this is positive quantity, and this is also a positive quantity, which means that the pressure at point 2 is less than the atmospheric pressure. So this pressure is a vacuum pressure. So this initial flow that we induced created a vacuum at point 2. So the water will flow from inside the tank to point 2 due to the difference in pressure, because this point is a vacuum. It's like a vacuum cleaner, so you're creating a small point of vacuum here. And as the fluid goes down, the height decreases and the pressure increases. Of course, the velocity is constant. So the decrease in the potential energy is transferred into an increase in pressure. So the pressure will keep increasing, but the fluid will flow due to the difference in elevation. And this explains what we saw in the video, and explains why the flow stops here. Because once the liquid level is a little bit below the inlet of the tube, air will go inside and will neutralize the pressure. So the pressure inside will be atmospheric pressure and the flow will stop. So this is an explanation why this phenomena happens. This is the last application that we are going to discuss. In the next video we are going to start discussing other things related to Bernoulli equation. So I'll see you then, inshallah. Goodbye.